Okay. Okay, so limits of functions. So limits of functions, so we have studied limits of sequences. So in limits of sequences, we had a sequence of numbers xn, which was tending to some limit L. So as n tends to infinity, limit of the sequence xn was some value L. Now what we'll have is, instead of the sequence of numbers xn, we'll have a sequence on f of xn. Okay, so in sorry, where was I? Yeah, so in sequences we had limit as n tends to infinity xn was equal to some value L. Now we are going to look at not at limit of a sequence, but limit of some function as x, not xn, that's x tends to infinity, or x tends to any value for that matter, not just infinity, any finite value for that matter. For any particular value x tending to c, we are going to look at what happens to the value of this function. So the intuitive idea of a function having a limit L at point C is that the values f of x are close to L when x is close to C. The crucial thing is, but different from. So I'm not talking about what happens to the function at exactly C. So suppose I'm looking for limit x tending to 0, x upon 2x. Okay, so if I put exactly x equals to 0, this thing becomes not defined. Okay, so if this were my function f of x, which is x by 2x, then what happens is that the domain of this function, the domain of f, does not include x equals to 0. X equals to 0 is not a point in the domain at all. So I am not interested in what's happening at x equals to 0. I am interested in what's happening as x becomes closer and closer to 0. So before we reach there, we have to look at a few definitions, which I'm quickly going to define on sets. So suppose A is a subset of real numbers, then we say interior point of set A. So these words are going to be very intuitive. Okay, so these definitions are going to be very intuitive. So an interior point is something which lies inside the set. So even if you did not knew the definition, okay, I've not talked about this definition yet, but let's say I just ask you, suppose this is the real line, and we have a set A which is 2 to 3. Okay, so A is open set 2 to 3. So what is an interior point? So an interior point is something which is inside here, right? So something which is between 2 and 3. So x, so 2 less than x less than 3 is the set of all interior points, and that intuition is correct. Okay, the intuitive logic to define interior points is correct. So here we are saying that any point x is an interior point of A if there exists a delta positive such that x minus delta to x plus delta, neighborhood of x, is inside A. So for any interior point, so all these points are interior points of my set A. So let me pick any one of them. Let's say this one. So for this interior point, you can construct, if this were x, then you can construct x minus delta to x plus delta, which will be completely inside the set 2 to 3. Okay, so there exists delta positive such that x minus delta to x plus delta is a subset of my set A. Then x is an interior point. Okay, I don't want you to remember these definitions. I want you to understand these words because sometimes in a paper they will be mentioned as a passing note. Okay, so they'll tell you what is the limit of this function at some interior point x. Okay, and at that point, if you stop and keep thinking about what's an interior point, you might get stuck. Okay, so there's nothing beyond logic here that somebody's talking about. Okay, isolated point. So an isolated point is something which is away from. Okay, in interior point, if I take closed sets, by the way, if I take a closed set 2 to 3, then all x, the same definition still holds for an interior point. 2 and 3 are not interior points, they are on the boundary, so they are not inside. So you can think of interior points as in terms of geography. So what are the interior states of India? So if you look at the map of India, the interior states are going to be states which do not have any international border or are not do not have a coastline. So something like Chhattisgarh. So Chhattisgarh is an interior state, or Madhya Pradesh is an interior state. Okay, so these are completely contained inside. So they have no boundary with other nations or no sea boundary as such. So that is something like an interior point. An isolated point is something which is isolated from the rest of the points. So it is not neighboring any other point. So these are interior points. If you want to imagine isolated points, you can think of a set B, which is, let's say, close 2 to 3 union 4. Okay, so the same set union this point 4. So this 4 is away from all the other points. All the other points in this set are here. This point is separated away from all the other points. It is not connected to any other point. So the technical definition here is that x is an isolated point if there exists a delta positive such that x is the only point in A that belongs to this interval. Okay, so you can construct a delta positive interval here such that this point 4 is the only point inside the set A lying inside the interval, this particular interval. Okay, so coming back to the map of India, can you think of any union territories or states which are isolated points, which are isolated from all the other states or union territories?
Andaman and Nicobar.
Very good. Andaman and Nicobar is a correct answer. There's one more. Not really a geography question, but I mean, we are not learning geography here, but if you can remember one more point, which is an isolated point. Nobody? Other group of islands starts with L. Have you all forgotten? Sorry, Vijay?
Lakshadweep.
Yeah, Lakshadweep. Very good. Okay, so that's the idea here. Okay, so an isolated point is something which is separated from all the other points. Now, a boundary point of A is that for every delta positive, the interval x minus delta to x plus delta, it contains points in A and points in B. So boundary point of this set, suppose you look at this set. So boundary points are basically points which are on the boundary. So 2, 3, and 4. These define the boundaries in some sense for this particular set B. So a boundary points definition is that if you construct for any delta positive, if you construct this interval, it will contain points inside A and points outside A. So let me erase this thing completely and let's focus on the boundary points 2 and 3. So if you construct any interval here, you will have the right parts are inside the set, the left parts are outside the set. Okay, similarly, if you construct any interval around 4 is also a boundary point, because if you construct this interval, all these points are outside the set except point 4. Point 4 belongs to the set, right? So you are okay as long as there's any point in this delta neighborhood which lies inside the set. It need not be that the point must be different from the particular point that you started from. So all the points that you see in the definition of any set become the boundary points. So if we look at boundary points of India, So obviously isolated points are all going to be boundary points. So that is Andaman and Nicobar, and there's going to be Lakshadweep. Plus there's going to be a bunch of all the nations which we share boundary with other countries like Jammu and Kashmir, Rajasthan, Punjab, uh, Himachal Pradesh, and so on, all the northeast states. Then we have all the states along the coastline like Gujarat, Maharashtra, all the southern states, Goa, uh, and so on. So a lot of states are going to be, actually, we have more boundary states than isolated states. Mm, so that is the definition of a boundary. Okay, so these three definitions are very intuitive. The fourth definition is going to be something new, and this is something which is interesting. An accumulation point of A. An accumulation point is a point such that for every delta neighborhood around that point, it should contain points in A that are different from X. Okay, so it should not, whenever you construct any delta neighborhood around that point, it should contain points from inside the set, but not the point that you started from. Inside the set apart from, sorry. Yeah, inside the set apart from X. Okay, so let me look at this figure again. Let me again consider the set B, which is 2, 2, 3 union 4. All right, so it is this set 2, 2, 3 union 4. So the definition is that X, not necessarily in A, X is a boundary point if for all delta positive, there exists, for all delta positive, X minus delta to X plus delta has points inside the set other than X. So let us understand this with the help of taking different points. So my first question is 2 an accumulation point? Oh no, sorry, we are looking at accumulation points, not boundary points. Is 2 an accumulation point? Okay, is the point 2 an accumulation point? Let me ask this question to Kritika. Kritika, do you think point 2 is an accumulation point going by this definition?
Oh no, sir.
Why no? If I
Because
construct, yeah,
X minus delta, 2 minus delta will not lie in that.
okay, no, it says that it should have points inside the set other than X. It does not say that all points need to be inside the set. Okay, so if I construct any neighborhood, these points to the right are going to be inside the set. So that validates my definition. It does not say that the entire thing has to be inside the set. It says that this neighborhood should have some points inside the set other than X. Okay, so the right points are going to be inside the set other than X. Okay, so next I want to ask to Kashish. Kashish, do you think point 3 is an accumulation point?
No, sir.
Why no?
So same as you said here that inside the X apart from X, as this is a point of accumulation point. So, and if we do X minus delta and X plus delta,
Yeah.
then if X is 3, then this won't be a point.
No, it says that this set should have points inside the set. So as you can clearly see, the points to the left are inside the set. Right, so it is an accumulation point. So 3 is also an accumulation point. So this thing is true. 3 is also an accumulation point. Okay. Okay, definition is simply saying that if you construct any delta neighborhood, it could be this long or this long or this long, or it could be this long. This delta neighborhood, no matter how small or how long you construct it to be, it should have points inside the set apart from 3. I don't know if you guys are sitting with a notebook or not, but you should really be sitting with a notebook. Okay, so my next question is to Vinay. Do you think point 4 is going to be an accumulation point?
So no, since 4 is not inside the set.
4 is inside the set.
Okay, yeah, then it is accumulation point.
Okay, again, you're wrong. Because if I construct a delta neighborhood, like I said, you should construct some neighborhood and see. Think about this delta neighborhood, Vinay. Does it have points inside the set other than X?
No, sir.
No. So it does not have. So that's why it's not an accumulation point.
Yes, sir.
Okay,
Makes
so the
sense.
question is not if X is inside the set or not. The definition does not require X to be inside the set to be an accumulation point. In fact, we'll see examples where points not inside the set can also be an accumulation point. Okay. Next question to Yuvakshi.
Yes, sir.
Is 2.5 an accumulation point or not?
Yes, sir.
Yes, is 2.5. Yes, that's correct. 2.5 is an accumulation point because whatever neighborhood I construct around it, you will have points inside the set other than 2.5. Okay. So if I were to write down the set of all accumulation points of this set, it would be the set 2 to 3. Okay, so the set 2 to 3 is the set of all accumulation points of this set. Okay. Okay, now let me consider the set open 2 to 3 union 4. Okay, so let me consider the set open 2 to 3 union 4. My question is to Vijay. Again, this is the definition, Vijay. Okay, so my question again, question number 1 is to an accumulation point. Vijay, are you with us? Okay, seems like Vijay is having connectivity issues. So let's move to Kanishka. Kanishka, is 2 an accumulation point?
Yes, sir.
Yes, very good. Okay, so 2 is an accumulation point because if you construct any neighborhood like this, the right points are going to be inside the set. So even though 2 is not included in the set, it is still an accumulation point. Okay. So 2 will be an accumulation point, 3 will be an accumulation point, 4 will not be an accumulation point. Okay, a point like 1.9. This will also not be an accumulation point because if I construct a neighborhood very small around 1.9, it will have no intersection with the set. Okay, so if you construct a very small neighborhood around 1.9, it will have no intersection from the set. So obviously points to the left of 2 or right of 3 are not accumulation points. The only accumulation points are going to be points from 2 to 3, including 2 and 3. Okay, 2.5 again is an accumulation point. So for this set also, surprisingly, 2 to 3 union 4. For this set also, the set of accumulation points is closed 2 to 4. Okay, and for closed 2 to 3 union 4, again the set of accumulation points was closed 2 to 4. So for both these sets, the set of accumulation points is same.
So it will be 2 to 3, right?
Yeah, sorry, 2 to 3. Yeah, so 2 to 3. So one last question from accumulation points is, what is going to be the set of accumulation points for the set R minus 0? Open question to anybody who would want to answer.
It would be R
Very
set of all
good.
real numbers.
Yeah, very good. So it would be this entire set R. The entire set R is the set of accumulation points for this thing. Okay, because this set is basically going to look like this. Okay, so this is your set R, this is the point 0 which is missing from here. So you have this union this. So this thing is not included, only 0 is not included. So I just need to check at 0 if 0 is an accumulation point or not, and 0 is. If you construct any neighborhood around 0, you will have points around 0 which are going to lie inside the set apart from 0. So 0 is an accumulation point. So the set of accumulation points is R. Now the question is, why are we doing this? Why are we looking at accumulation points? We are looking at accumulation points because the limit of any function is defined not on its domain, but on the set of accumulation points of its domain. So when we talk about limit of a function, we don't want to ensure that the limit that we are checking at should be a point in the domain, but we need to check if the point is an accumulation point or not. Okay, so suppose a function is defined on this set. Okay, so if a function is defined on this set, even though 2 and 3 are not in the set, limit x tending to 2 f of x still makes sense. And even though 4 is not, 4 is in the set, limit x tending to 4 f of x does not make sense. Okay, so that's why we are interested in accumulation points. So the only thing that I want you to know is that sometimes when you're reading a textbook of higher algebra, or maybe you're appearing for an exam and the examiner just wants to, irritate you. And so you would give a word like limit x tending to c f of x, where c is an accumulation point of the function. Okay, so at that point, all you need to know is it's nothing new. Okay, it's nothing new. It is just your normal limits of function, so you need not worry about it. Okay, so maybe you have never heard about accumulation points, so I just wanted you to familiarize with the concept. Okay, so that's it about accumulation points and all these other points. So let's go to the definition of limits now, limits of function. So let f be a function defined from A to R, where A is a subset of R, and suppose that C is an accumulation point of A. Okay, so this is how the definition is defined. Then limit x tending to C f of x is equals to L if for every epsilon greater than 0, there exists a delta greater than 0, okay, such that 0 minus a mod of x minus c between 0 and delta, and x belongs to A implies that mod of f of x minus L is less than epsilon. Okay, so what does this mean? So let us understand this graphically. Let's say this is some function f of x, and I am analyzing its limit at some point c. Okay, so I'm claiming that my claim is that limit x tending to c f of x is equals to L. So if this value is, let's say, L, then what it says is that you can construct an epsilon neighborhood to L. So this becomes L plus epsilon and this becomes L minus epsilon. So what we are saying is that for all epsilon positive, so construct any neighborhood like here, there exists delta positive. What is delta? Delta is a neighborhood around C. So this is C plus delta and this is C minus delta. Such that mod of x minus C less than delta implies mod of f of x minus L is less than epsilon, which means that if you were to construct this delta neighborhood around C and this epsilon neighborhood around L, you would see that any map of a point in this band on the x-axis will map on this band on the y-axis. Okay, and these bands could be smaller or larger depending on what your assumed values of epsilon are. Remember, the story begins from here. You start with a band here, and corresponding to this band, you construct a band on the x-axis. So you say that any functional any x in this blue band will have its image in the yellow band. Okay, so image under the function for any point in the blue band is going to be in the yellow band. So that is what the definition of limits is. Again, I want you to know the definition. I don't want you to remember it. I want you to be able to understand the definition if you come across it in any textbook, but there is absolutely no need to be able to reproduce it in any exam. Okay, so you don't need to remember it. You just need to be able to understand if something as complicated as this is there in some textbook that you are reading. You should be able to read math. That is the aim. Okay, so notice that we do not consider what happens at C. Okay, so what happens at C becomes a thing if continuity. So we'll look at it in the next chapter, that is continuity. Right now, we are not interested in what's happening at C. We are only interested in what's happening around C. Proposition, the limit of a function is unique if it exists, easy to see from this particular definition. Let me construct another graph. So suppose a function looks like this. At some point C, to the left of point C, it's taking value L1. To the right of point C, it is taking value L2. So you cannot claim that these two are both limits. Because remember the definition. The definition is for all epsilon here. So you can have an epsilon here and you can have another epsilon here. But you should have a same epsilon around the point C. So for every epsilon, so let me say this is epsilon 1, this is let's say epsilon 2, and this is let's say delta. Okay. So corresponding to this delta, epsilon 1, suppose I have some delta 1 here, and corresponding to this epsilon 2 here, I have let's say some delta 2 here, which looks like this. So what I'm saying is that every point in the delta 1 region should be mapping in the epsilon 1 region here. And every point in the delta 2 region, which is a smaller band, all points should be mapping in epsilon 2. But if this L1 and L2 are not equal, if L1 comma L2 are not equal, if L1 is not equals to L2, then we can construct epsilon 1 comma epsilon 2 such that L1 plus epsilon 1 is less than L2 minus epsilon 2. So this point is L1 plus epsilon 1 and this point is L2 minus epsilon 2. So what we are saying is if L1 and L2 are not equal, we can take specifically small values of epsilon 1 and epsilon 2 such that these two bands, these two yellow and blue bands on the y-axis They do not intersect. And then what I'm saying is that for delta, which is the minima of these two deltas, so here it's the black one, which is delta 2. So all points here should be going here as well as here, because that's what the definition says. That definition says that for points sufficiently close to C, points should be going in this epsilon neighborhood. So we are putting a restriction on these points to be mapped here as well as here, which will not happen. Okay. So in a situation of discontinuity, so later on in the chapter, we'll see this as a discontinuity at C. So in a situation of discontinuity, we do not say that this function has two limits. We say that the limit of the function does not exist. Okay. So that's the proposition. The limit of a function is unique if it exists. So this is the entire proof in words for the same thing. Okay, now the next theorem is that if F is A to R, where A is a subset of R, and suppose that C is an accumulation point of A, then limit x tending to C f of x is equals to L if and only if limit n tending to infinity f of xn is equals to L for every sequence xn in A with xn not equal to C, such that the sequence itself converges to C. Okay, so here we are defining, here what we are doing is defining limits of a function or limit of a function using limit of a sequence. Right, so we are defining limit of a function using limit of a sequence. So what are we saying here? Again, let me draw a graph with some function like this. So at some point C, the limit is L. So the definition says that take any xn, any sequence xn tending to C. Okay, so take any xn which is tending to C. So let's say this is my sequence xn which starts from here and tends towards C. Okay. Then the sequence f of xn will be tending to L. Now, what is the sequence f of xn? So sequence f of xn is the sequence of images of this function. So let's say this point is x1, so this point becomes f of x1. If this point is x2, so the image of x2 becomes f of x2, and so on. So you will have a sequence which gets constructed on the y-axis, which is the image of this sequence on the x-axis. So this sequence, let me call this as the sequence yn, which is basically the sequence f of xn. Okay, so this sequence f of xn will be converging towards L, provided that this sequence does not have any of its elements as C. Because you see, if the function is not even defined at C, suppose this function is not defined at C, okay, then you can get a not defined thing for f of xn. Okay, so you don't want that. So that's the relationship between sequences of functions and sequences of limits of sequences and limits of functions. We define a new function now, which is called the Signum function. So what is the Signum function? So Signum function, a very nice function. It just reports a value 1 if x is positive. It reports a value 0 if x is 0. It reports a value -1 if x is negative. So Signum function's graph looks like this. So this is the y-axis and this is the x-axis. It takes a value 1 for all positive x, takes a value -1 for all negative x, and takes a value 0. So this is going to be your signum function like this, this, and this. Okay. All right. So the limit x tending to 0 signum x does not exist. Okay, so limit x tending to 0 signum x does not exist. Why does it not exist? Because this is my signum function, right? So if I construct, so I'm interested in finding limit x tending to 0 signum of x. So if you construct any, so we do not say that the limits are 1 and -1. Because again, the same logic, you can construct epsilon neighborhood here and epsilon 1 neighborhood on the positive side and epsilon 2 neighborhood on the negative side. But for any corresponding neighborhood here, you cannot have points mapping both here and here. Okay, so that will not happen. So this thing does not exist. Okay, so we do not say that it has two limits. We say that its limit does not exist. By the way, such functions are told to have a jump discontinuity. So a jump discontinuity is when functional values jumps. So here we see that the functional value jumps from -1 to 0 and then again from 0 to 1. Okay, so it jumps up, function jumps up. So it's called a jump discontinuity. Okay, now some important functions. So limit of 1 by x as x tends to 0. So as x tends to 0, 1 by x ka limit does not exist. And sine 1 by x also does not exist. So let's look at the graphs of 1 by x. So 1 by x will basically look like this. Okay, so this is x, this is y, and this thing is y equals to 1 by x. 1 by x. So it goes to positive infinity towards the positive 0 side. It is going towards negative infinity on the to the left of 0. Okay. So this limit does not exist as it's going to infinities. Sine 1 by x also does not exist because as 1 by x becomes larger and larger. So as x goes to 0, 1 by x increases in magnitude. So this sine 1 by x, it will oscillate. You see, sine function is an oscillating function. As you keep increasing its input value, it will start oscillating. So this is the diagram of sine 1 by x. This is a zoomed out version. Okay, this is 0, 1, and so on. When you zoom into it, when you zoom into this particular function, you get this thing. Here you can see the variances from 0 to -0.05. So as you can see, it oscillates and it starts oscillating very, very fast as you keep reducing your value of x, and that's going to be the nature of this particular function sine 1 by x. Okay, so sine 1 by x, it does not have a limit. Okay, next we look at some types of functions which are called as bounded functions. So we looked at bounded sequences. So a sequence which has an upper bound and a lower bound is called a bounded sequence. So similarly, we have bounded functions. So functions which have a maxima and a minima are going to be called as bounded functions. Okay. So first we define the supremum and infimum of a function. Okay, a supremum of a function over any set A is basically the supremum of all the values of f of x defined on the set A. Okay, so it is something which is greater than all the functional values. Okay, so it is going to be the slightly greater than or equal to all the functional values. So suppose you define a function f of x equals to x on the set 0 to 1. So the supremum of this thing is going to be 1. And the max of this thing is also going to be equal to 1. Okay, so the max of this function is 1. On 0 to 1, the max happens at 1 and it's going to be equal to 1. So this is my function, right? 0 to 1. X, f of x. But if on the other hand, you were to define this function on open 0 to 1, then again the supremum is 1, but the max of this function does not exist. Here we say the maximum, the function does not have a maximum. Okay, so maximum may or may not exist, but the supremum always exists. Okay, so this is a bounded function. It has a bound in the sense that it has a ceiling above which it does not go. It has a floor below which it does not go, right? It does not go below 0. It does not go above 1. So it is bounded between 0 and 1. But this function does not have a maximum. This function does not have a maximum because you want to believe that the maximum is 1, but 1 is never achieved because this function can take a value 1 when it reaches 1, but 1 is never being reached. So we say that this function here, in this example, it does not have a maximum, but it has a supremum. The supremum is still 1. The definition of supremum is something which is greater than or equal to all the functional values, and there is no other function, no other number like this. Okay, so supremum of a set A is equals to a value is equals to m, implies m is the smallest number such that m is greater than or equals to x for all x in the set A. So for all the elements in the set A, m is the smallest number which satisfies the property that it is greater than or equals to all the numbers. So here, for this particular function, the range of this function is also 0 to 1, which is this one. The range is also open 0 to 1. So the supremum is 1 and the infimum is the number less than or equal to all the values in the set such that it is the largest such number. So that is going to be 0. So the infimum of this particular function is going to be 0, even though the min does not exist. So that's why using supremum and infimum is a more general thing, because you can have functions which do not have a maxima or minima, but roughly speaking, it is going to be maxima or minima. Okay, so roughly speaking, supremums and infimums in raw language, you can basically replace the word maximum or minimum for supremum or infimum without causing any problems. Okay. So then we have a bunch of functions for which you need to find the supremum and infimum. Okay, let's look at this function. Function defined on 0 to 2. Okay, so this should have been 0, 2. I don't know why I've written colon. Function defined on 0 to 2 such that f of x equals to x squared. What is going to be the supremum and what's going to be the infimum? Anyone? It's not too difficult. Anybody can just switch on your mic and you can give me the answer.
Supremum is 4 and inferior is 0.
Yeah, infimum. Okay, infimum is 0. Very good. So it's the smallest value. What about this function? Somebody else, anybody wants to chip in? What is going to be the supremum and the infimum?
Zero and 1. Infimum 0 and supremum 1.
Okay, so 0 and 1. Does everybody agree to this? I see some of you making some activity with your mic. That's not true. Okay, so I'm not looking for the supremum or infimum of this set. I'm looking for supremum or infimum for f of x values. Okay, so the f of x values for 0 and 1. So as x goes to 0, what happens to 1 by x? It goes to infinity,
It
right?
becomes not
So
defined.
it goes to infinity. It increases, not defined, but yeah, it keeps on increasing. So the supremum here is not defined. Okay, it does not have a supremum. The infimum is going to be 1. 1 is the infimum. 1 is the smallest value you can achieve for 1 by x on this set. Okay. So in this particular situation, we say that the function is not bounded above. So this is an unbounded function. When it has both the supremum and infimum, we call it a bounded function. Okay. All right, so these things, they are in the passing. You might encounter these terms in some problem and you might think, okay, what's a bounded function? So bounded function is something which does not go to infinity and does not go to negative infinity. That is the simplest meaning of a bounded function. So even if I knew nothing about supremums and infimums, I just wanted to tell you what's important here. The important thing here is a function is bounded if it does not go to infinity or negative infinity. That's it. Okay, so if you can just remember that much, that is sufficient. All right, now left and right limits. So we first look at left and right limits. What are left and right limits? A function a tending to r, where a is a subset of r, and c is an accumulation point of the domain of this function. Then f has the right hand limit x tending to c plus f of x equals to f is equals to L if for every epsilon positive there exists a delta positive such that this thing holds. Okay, so now we are saying that the right hand limit is for all x values strictly greater than c. So remember this graph I drew earlier about a function which had some sort of a discontinuity here. So if this were point C, so when we analyze the right hand limit, we are going to only analyze points to the right of C. And we look at what happens to the functional values to the right of C. Okay, so I know that functional values are going to tend towards C. So if I take any sequence which is basically moving towards C from the right, the image sequence is going to move towards L from top. Okay. On the other hand, the left hand limit is going to be points to the left of C, which are going to be denoted by, let's say, a sequence which goes towards C from the left. So for such things, you will have this L prime, and you will see that the points, the image sequence is going to be tending towards L prime from bottom. So in such a case, what we say is that the left hand limit of f of x tending to C is L prime, and the right hand limit of f of x tending to C is going to be L. So left and right hand limits are going to exist here, even though the overall limit does not exist. Okay, so limit. So sometimes to clarify, you write the left hand limit as x tending to C minus and x tending to C plus. Okay, limit x tending to C plus. So that's how you clarify the reader between left and right hand limits. So even though limit x tending to C f of x does not exist, but the left and right hand limits individually, they exist. So we saw this another function, Signum function. So for the Signum function, this is what the Signum function was like. So at 0, the right hand limit is +1 and the left hand limit is -1. Okay, so we say that limit x tending to 0 plus signum x is 1. So this is your right hand limit. And limit x tending to 0 minus signum x is -1. So let's do an example here. Find the left and right hand limits for the function f of x equals to x square by x. Okay, so x square by x is not the same as x. Okay, so x is going to be defined at 0. X square by x is not defined at 0. So that's why I'm giving you the function x square by x at so x square. No, wait, let me make it mod x by x. Mod x by x, that's good. Okay, function mod x by x at 0. Okay, so I'm interested in the left and right hand limits at of mod x by x. So I'm interested in limit x tending to 0 plus, this is the right hand limit, of mod x by x equals to, and limit x tending to 0 minus mod x by x equals to. Okay, so first question goes to Kashish. Kashish, limit x tending to 0 plus mod x by x. What is this going to be equal to?
0.
Not going to be 0. Let's say x is 0.001. Okay, so this is mod of 0.001 upon 0.001. So what is this value? What is this value, Kashish? Hello, Kashish.
Yes, sir.
What is this value?
So is it going to be 1?
Yes, it is going to be 1. Okay, so it's not that it's going to 0, so you say okay 0. Okay, that's not how limits work. Okay, so what you have to do is here that since x is 0 positive, so mod x is going to be x. Okay, since the number that I'm assuming is positive, so this becomes x by x, and x by x, as long as x is non-zero, so we are finding limit at 0, which means that x cannot be 0. So as long as x is not 0, this becomes equal to 1. Okay. Okay, next question goes to Vinay. What is going to be this limit? Very good, -1. Okay, so this is going to be -1 because when x is negative, minus mod of x becomes minus x upon x, so this becomes -1. Okay, so these are going to be left and right hand limits. This is basically Signum function. Okay, so this is basically Signum function. This is the definition of Signum function at x not equals to 0. At x0, you just say Signum function is 0. So that becomes your complete definition of Signum function. So we say that this proposition is basically the most important thing, that limit x tending to c f of x is L if and only if. If and only if is very important thing to say. Okay, if and only if का मतलब है that if left and right hand limits are both L, then this thing is L, and if this thing is L, it means both these things should hold. Okay, so if I establish that the left and right hand limits are equal, I have essentially established the limit of a function. Now, why is this proposition very important? Is because a lot of questions that I'm going to encounter in limits of functions are going to play around this modulus thing like I did here. Okay, I played around the modulus. I gave you things like this and that, and then asked you what's going to be the limit, left and right hand limit. So a lot of times he's not going to ask you left and right hand limits. He's going to simply ask you find limit x tending to 0 mod x by x. He's going to ask you this thing. He's not going to ask you limit for left and right hand limit. But here, because mod comes into the picture, what happens, the story to the left and right is going to be varying. So you have to yourself assume that you have to find out the left and right hand limits. Find left and right hand limits. If they are both same, great, limit exists equal to that thing. If they are both different, like happening in this case, then we say that the limit does not exist. Okay, let's look at these functions now. G of x equals to e to the power 1 by x. So let's find the left and right hand limit for this function. So at left hand limit, okay, at x equals to 0. I should have written this. Left and right hand limits at x equals to 0. So at 0 plus, what happens at 0 plus is this thing becomes positive infinity. So it will go to infinity like it's happening. Okay, it's going towards infinity. At 0 minus, what happens is this becomes e to the power negative infinity. Okay, so g becomes e to the power negative infinity time kind of thing, which is basically 1 by e to the power infinity. Now e to the power infinity is infinity, so this just becomes 1 by infinity type of a thing, which is 0. When you divide 1 by infinity, you get 0. So that's what we see. So this function, it looks like this. Okay, so it is approaching 0 to the left and infinity to the right. So we say that the limit does not exist. Okay. Now, once you know that, you can find this thing also, right? So 1 by e to the power 1 by x plus 1. So I know that e to the power 1 by x. Okay, so I have 1 by e to the power 1 by x plus 1. Okay, so at 0 plus, this thing is infinity. So 1 by infinity plus 1 is 0. And at 0 minus, I know that this thing is 0. So 1 by 0 plus 1 becomes equal to 1. Okay, so as you can see, at 0 minus, this thing is becoming 1. At 0 plus, this thing is becoming 0. So this is how you can basically check the different limits at different values. Now, till now, we were looking at functions and what happens to its limit as x tends to a finite value, 3, 4, or 0. Mostly we look at 0, but I'm going to give you examples where we are going to look at something other than 0 also. But now we look at situations where we do not look at 0, but we look at what happens to the functional values at infinity and negative infinity. So let's say the limit of this function is at x tending to c is, okay, so there are two things, the limit going to infinity and x going to infinity. So we first look at infinite limits, when the limit, that is the function, becomes infinity. So we say that f tends to infinity as x tends to say, and write it like this. Okay, so this just implies that as x begins to go towards the value c, my function goes towards infinity. Okay. So this is an example. So you look at 1 by x square. So for 1 by x square, the right hand limit and the left hand limit both are going towards positive infinity. So we can say that limit x tending to 0, 1 by x square is equals to infinity. But if you look at 1 by x, the right hand limit is positive infinity, but the left hand limit is negative infinity. So these two things are different. So in this case, we cannot write it like this. We have to say that limit does not exist. Okay, so writing it like this would be wrong. Although we can write that limit x tending to 0 plus 1 by x is equal to infinity, and limit x tending to 0 minus 1 by x is equals to negative infinity. So these two statements are correct. And if I want to write at about overall limit, I have to write at the overall limit does not exist. Okay. Okay, now a very interesting example is f of x equals to x sine 1 by x at x tending to 0. This example is interesting because I've already looked at sine 1 by x and I've established that sine 1 by x is an oscillating function. But this function is still bounded. It is bounded in the range -1 to 1 because sine of anything is between -1 to 1, right? We know that. So sine function cannot be going towards infinity in magnitudes. It is bounded between 0 to 1. Okay, so x times sine 1 by x as x tends to infinity, as x tends to 0. So as x tends to 0, this thing becomes 0. This thing is bounded. So you have 0 multiplied by something which is finite. Now 0 multiplied by anything that is finite has to be 0. Okay. Actually not 0. This becomes 0. So this is like tending to 0 multiplied by something finite. Not absolute 0. Because like I told you, x tending to 0 implies that x is not equals to 0. So this is not x equal to 0. This is x becoming closer and closer to 0. And it gets multiplied by something which is bounded in the range -1 to 1. So it has to be 0 into something finite, and that becomes 0. Okay. But let's look at this function 1 by x sine 1 by x. Now this part is oscillating, whereas this part is going towards positive or negative infinity. So this part is oscillating between -1 to 1. So it can be both positive or negative. Whereas this thing becomes at 0 plus, this thing I know is going to positive infinity. So positive infinity multiplied by something which can be positive or negative means that this function itself can be both positive or negative. So I cannot comment anything on this particular function 1 by x sine 1 by x. It can go anyway. The same holds for this thing at negative also. This thing goes to negative infinity, but this can be both positive or negative. So the multiplication can be both positive or negative. So here what we are saying is that for 1 by x sine 1 by x, the left and right hand limits are also non-existent, and the overall limit obviously non-existent. So this does not exist, this does not exist, this does not exist. So for 1 by x, we had left and right hand limits existing at positive and negative infinity, but overall limit did not exist. Here, we don't have the left and right hand limits either. So that's the difference. So this was the part where the limits were becoming infinite. Now we look at what happens to limits at infinity when x goes to infinity or negative infinity. Okay, so first we define this thing. So what is the definition of limit x tending to infinity f of x, or limit x tending to negative infinity f of x? Okay, so this should be negative sign. There should be negative sign. Anyway, so what is the meaning of this? So this means that for any positive epsilon, there exists a k greater than r, such that for any x greater than k, mod of f of x minus L is less than epsilon. So let's look at the meaning of this statement. What does this statement mean? So again, I'll draw a graph and try to explain this graphically. So let's say this is a function which is going towards infinity, going towards this value L at infinity. I should draw it a little lower. So what the definition says is you can construct an epsilon neighborhood around L minus epsilon to L plus epsilon. Now, corresponding to this epsilon neighborhood here, you can find a cutoff point here, K, such that for all values of x greater than K, for all x greater than K, f of x, sorry, mod of f of x minus L is less than epsilon, which means that you take any functional value greater than K, it will be lying inside this yellow zone. That is the meaning of limit at infinity. This is the definition. Obviously, again, I don't want you to remember the definition. The point is, in our 11, 12 textbooks, mostly in most of the textbooks, everything was defined in words. In words, the definition is very straightforward. You know, the definition in words is as x becomes too large, the functional value tends to L. Okay. The problem is this is not how things get defined in real life. So now that you will be learning higher level economics and maths, you'll be handling textbooks which won't define things verbally at all. Like you'll be starved for words. You'll be like, kuch to word to likho. Okay, so everything would be in such abstract terms, and I want you to be comfortable with that. That is my aim here, because see, our relationship lasts for only a year. You go into your colleges, and then a lot of times you are uncomfortable with the way things are being taught in these colleges. These colleges, they don't give you time to adapt. Okay, so I want you to be comfortable with this language. This does not have a very this does not have a lot of benefit from the exam point of view. This has a benefit from your post-exam point of view, that after you go into your masters, you should be able to handle the literature that they hand you. Okay, so this is basically saying that for all x values coming after K, the functional value should be mapped in this region. That is the definition of limit x tending to infinity f of x equals to L. Okay. So we looked at 1 by x. So x tends to infinity as 1 by x. So this is when x, so as x tends to infinity or negative infinity, functional value becomes 0. Okay, so this is f of x. Right, so this f of x, as x tends to positive infinity, this becomes 0. At the same time, as x becomes negative infinity, this becomes 0. Okay. So corollary for this thing is that limit x tending to infinity f of x can be defined as limit t tending to 0 plus f of 1 by t. Okay, so a lot of times you can convert limits by making substitutions. So you have some limit of x going to infinity, you don't like that, so you can convert it to x going to 0. So to understand this, let us look at this particular example. Okay, so I am given a function which I have to derive the limit as x tending to positive infinity. So instead of what I can do is I can write this as limit t tending to 0 plus, now x becomes 1 by t upon under root 1 plus 1 by t square. Okay, so this becomes 1 by t times under root 1 plus 1 by t square. Then this t goes inside, this becomes 1 by under root 1 plus t square, limit t tending to 0 plus. Now as t tends to 0 plus, now you see as t tends to 0 plus, you can make the substitution 0 plus. Okay, I can make the substitution 0 plus, and this becomes 1 by under root 1. So this becomes 1. Okay, so this is going to be the holy grail of when to do substitution. So my question is, when to substitute? When do I substitute the value x equals to 0? Why did not I substitute the value here? Why did not I substitute the value here, and why did I substitute it here? So this is the most important thing in limits. When do you substitute? So you should substitute when you see something that is not of the format 0 by 0 or infinity by infinity. If you see something of this format, you cannot do substitution. So for example, if you look here, x and 1, as x tends to infinity, both x and 1 by x, 1 plus x square are going to infinity. So this is infinity by infinity format. So I cannot substitute. Okay. Similarly, if I look here, sorry, where was this? Yeah, if I look here, this 1 by t, as this goes to infinity, this is infinity. Okay, and this is also infinity because 1 by t square is infinity, so this is also infinity. So this is still infinity by infinity format. Okay, what is the problem with this thing? The problem with this thing is, this is, the numerator is fine. It is the denominator which has an issue. The denominator is this thing, t tending to 0 plus. So this is 0, and this thing is infinity. So this is 1 by 0 into infinity. So this is another class of problems that you can encounter. 1 by 0 into infinity, or 0 into infinity by 1 format. 1 or k, any finite value k. So these are the classes of things. If you see, you cannot do substitution. So try to, so the aim is going to be to go from such a format to something which does not look like this. So for example, I'm looking at limit x tending to 0 plus x square by x to power 4. Okay, now obviously I cannot do a substitution right away because this becomes 0 by 0 format. So not applicable. So what I need to do is I need to do some algebra on it and see what happens. So obviously I can cancel x square on both the numerator and the denominator. So this is equal to limit x tending to 0 plus x square upon x square into x square. This cancels with 1. So this becomes limit x tending to 0 plus 1 by x square, which is basically positive infinity. Right? Because this is no longer any of the taboo formats. Okay, so the taboo formats are going to be 0 by infinity, sorry, 0 by 0, infinity by infinity, then you have infinity into 0 by 1, or 1 by 0 into infinity. So these are going to be some of the taboo formats. Okay. All right, some simple properties of limits. If one function is always less than the other function, the limits of the lower function is always going to be smaller. If a function g of x is sandwiched between f and h, then the limit of and the limit of both these functions is L. So f of x is also L and g of x is also L, then sorry, h of x is also L. Then g of x has no option but to have a limit L. So this is the sandwich theorem. Then certain algebraic properties of limits. If f is 10 has a limit L, g has a limit M, then k times f function will have a limit KL. Okay, so I've seen that limit x tending to 0, x by x is equals to 0 plus x by x is equals to 1. So this implies that limit x tending to 0 plus 2x by x will be equal to 2. Okay, so I'm just multiplying this function with 2. So I can take this 2 outside and you can write this here. So 2 times limit, and that is 2 times 1, so that is equal to 2. So these things can be taken out. Okay, so when you multiply any function with a constant, the limit gets multiplied by the same constant. When you add two functions, okay, so if I want to find limit x square plus x by x, x tending to 0. So you can break it down as limit x tending to 0, x square by x plus limit x tending to 0, x by x. So this question is to you, Akshi. What is going to
Yes,
be
sir.
this limit? You have to break it down into two different limits here. Are you here with us, Ryuakshi?
Sorry, sir, I'm not able to answer.
What is going to be this limit first of all? Limit x by x as x tends to 0.
1?
Yeah, 1. Okay, because they cancel out, we get 1.
Yes.
Okay, can you reduce this limit x square by x? Reduce into something like do some cancellations and reduce into
And
something.
it will be limit x tends to 0 into x.
Limit x tends to 0, x. So what is what happens to x as x tends to 0?
It becomes 0.
0. So what is 0 plus 1?
So 1.
Very good. All right. Let's look
Sir,
at, yeah.
Sir, I had this question. When we have to do this LHL and RHL part, that's why I was getting confused. Like if in this part only I have to do the RHL and LHL simultaneously.
This comes by experience. So my experience is when you see modulus things, you have to go for left and right hand limit because modulus gives different results to the left and right of some particular value. So when you have modulus in your functions or squares in your function, in that situation, you might have to use left hand limit, right hand limit. See, the problem is that it's not defined that this is when you use this. It has to come from experience, because if there was a set of rules which you could follow and do every question, I would have given you those set of rules. We will not be doing problem sets, right? So you have to do problems. There's sadly no shortcut here. You have to do problems and you have to gain experience. Kis question mein kaisa chalega. So a lot of problems you do, you're going to reach dead ends. You will apply one technique and you see, okay, it's not getting solved by this technique. Then you'll apply some other technique. And that's how you're going to learn. Okay, so that is the only way to learn. All right.
Yes.
Okay, so let's look at these limits now and try to solve them. So I'm giving you let's say what is 5:23 right now. So why don't you take 7 minutes, do as many as you can. Okay, so I hope you can see everything. So I'm giving you till 5:30 to solve this and then we'll discuss them. So limit x tending to 1 plus. So as x tends to 1 plus, this thing is going to 1 and this thing is going to something greater than 0. Okay, slightly greater than 0. So this becomes 1 by 0 plus format, which is basically infinity. Okay, so if it is 1 by 0 plus type of format, you don't have to apply anything. You just directly look at 1 by 0. 1 by 0 is infinity. So you don't have to do anything else apart from this. Okay, so that's question number 1. So this will go to infinity. Let's look at B part. X upon x tending to 1, x upon x minus 1. So I already know that the right hand limit is positive infinity. If I find out the left hand limit, I can find out the limit of this thing. Okay, so so Kanishka was asking about L'Hopital. So L'Hopital is not even applicable here. Okay, so L'Hopital we'll see later on. It's a shortcut method sometimes when you have this 0 by 0 format or infinity by infinity format. It's not applicable in questions like here because you don't have a 0 by 0 or an infinity by infinity format. Okay, so to analyze this, we need the left hand limit to this thing. So the left hand limit is going to be 1 by 0 minus. So that is going to be negative infinity. So negative infinity is the left hand limit, right hand limit is positive infinity. So this limit does not exist. Let's look at the C part. C part is right hand limit to x plus 2 by root x. Okay, so x plus 2 upon root x. So I want to ask this to Kritika.
So
Kritika.
I haven't.
Okay, no problem. I am just asking you what happens. Okay, so this is limit x tending to 0 plus. What happens to the numerator as x becomes 0? What is 0 plus 2? Kritika, come on.
It's 2.
And what happens to root x as x becomes 0?
It's 0.
So what is 2 by 0?
Infinity.
So that's all you need to do. Okay, so so this is the infinity, positive infinity, in fact. Okay. The next up, they are asking you the same thing for x tending to infinity. Okay, so this is going to be interesting. So x tending to infinity. So Vijay, have you done this one? Vijay, are you with us? Hello, Vijay. Okay, I don't know. Okay, Vinay.
Sir, I noted as root x plus 2 by root x as x tends to infinity.
Sorry, I can't hear you properly. What's going to be this one?
I wrote it as root x plus 2 by root x.
Very good. Root x plus 2 by root x. Fine. What happens to root x as x tends to infinity?
It tends to infinity.
And what happens to 2 by root x as it goes to as x goes to infinity?
It goes to 0.
And what is infinity plus 0?
So it's infinity.
Infinity. Okay, so that's the answer. Okay, that is the answer to this one. Okay. So Yuvakshi, you're up next.
Yes, sir.
Yeah. So do you have this limit x tending to 0 for under root x plus 1 by x?
No, sir, I wasn't able to do.
Okay. What happens to x plus 1 as x tends to 0?
It becomes 1 and then positive. So it will
Becomes
be
1.
infinity.
Yeah, it is just 1 by 0, which is infinity. Okay, so it's very straightforward. Okay, Kanishka, what is x tending to infinity, this thing? Under
So
root x.
I took x common Then
Okay.
x under root 1 upon x plus 1 upon x square.
Yeah.
And x cancel with x. So we are left with under root 1 plus 1 upon x square. And this is 0 when we put infinity over it
Yeah. Very
in
good.
place of x.
Very good. Okay. So she basically divided, took the x square underneath the under root. So she gets x plus 1 by x square. Then you can split it. X by x square is 1 by x, and 1 by x square is 1 by x square. So you can add them up, and this is 0, this is 0, so this becomes under root 0 plus 0, which is basically 0. Okay, so this is going to be 0. Okay, who's next? Kashish, part G.
So I was not able to solve this.
Okay, under root x minus 5. You guys are finding good excuses to not solve it. I mean, you will not get the excuses in exam. Under root x plus 3, limit x tending to infinity. Okay. So here you have to try some things. What did you try? What did you try, Kashish? What have you tried here? You tried doing anything?
So like I kept like in part of x I kept 1.
Sorry,
In term of x root x I kept 1.
why did you keep 1 here?
I was trying.
Okay, x is going to infinity. First of all, you need to do infinity. What is infinity minus 5, Kashish? What is infinity minus 5?
5.
No, infinity is a very large number. Infinity minus anything is infinity. Okay, so infinity, unless it is infinity minus infinity. So infinity minus 5 is infinity, and infinity plus 3 is also infinity. So this is basically infinity by infinity format. So first of all, we have to figure out what format is this function in. If it is something other than infinity by infinity, or those 4 formats that I talked about, if it's something else, then we can't do anything. So first of all, I figured out that this is infinity by infinity format. So I cannot do substitution. Okay. If it were something like infinity by 1, then it would be infinity. If it would be like 1 by infinity, it would be 0 or something like that. But it is not. All right. It is infinity by infinity. Infinity minus 5 is infinity. Infinity plus 3 is also infinity. Infinity is a very large number. You subtract a few drops from an ocean, the ocean doesn't become small. That's the idea. Now this is infinity by infinity. So what I can do is I can divide both things by root x. Okay. So as x tends to infinity, what happens to root x? Kashish, all questions are going to be directed to you. What happens to root x, Kashish? As x becomes infinity, what happens to root x?
So infinity.
Very good. Okay. So I can replace this root x with t. All right. Then I can divide. Then what you can do is you can basically divide both the numerator and denominator by t. All right. So I get limit t tending to infinity, t minus 5 by t upon t plus 3 by t, which is basically limit t tending to infinity, 1 minus 5 by t upon 1 plus 3 by t. Okay. As t tends to infinity, Kashish, what is 5 by t?
So infinity.
No, what is 5 divided by infinity? What happens when you divide 5 by a very large number? Kashish?
So infinity.
No, when you divide by a very large number, it becomes 0. So this is 1 minus 0 upon 1 plus 0. Okay, so dividing by a very large number gives 0. What happens to 1 by x as x tends to infinity? It is 0, right? 1 by x goes to 0 as x tends to infinity. Okay, so phi by t is going to be 0. Now this is becomes 1 minus 0 upon 1 plus 0, which is basically 1 by 1. So that is 1. Okay. Okay. So this thing becomes 1. All right. Now this is the final thing. Root x minus x upon root x plus x. Limit x tending to infinity. Root x minus x upon root x plus x. This is going to be equal to. So again, this becomes infinity minus infinity upon infinity plus infinity format. I definitely cannot solve it right now. So what I need is to remove something. So what I do is I take root x common. So this becomes limit x tending to infinity root x times 1 minus root x upon root x times 1 plus root x. Okay, so these root x's, they cancel out. So what you are left with is limit x tending to infinity 1 minus root x upon 1 plus root x. Okay. Now, after this point, you can basically see that this is going to be negative infinity by negative infinity. So you can again divide by root x. Divide the numerator and denominator by root x. So you have to keep trying something. Okay, so you cannot ask me ki ye kaise kiya. This is experience. This is what you have to try. You need to write stuff down. Okay, there is no easy way. This is what I keep saying. And the problem is not that I'm not teaching you something which is there. The problem is that you have to attempt these problems and you have to learn by doing. So when you divide by root x, this becomes 1 by root x minus 1 upon 1 by root x plus 1. Limit x tending to infinity. So this becomes 0, this becomes 0, so this becomes 0 minus 1 upon 0 plus 1, so that is minus 1 by 1, so that is minus 1. So this is the answer here. All right. So that's limits for you. Now, final thing is continuity. So continuity is a very straightforward thing. So the basic idea of continuity is that the proposition, I'm just jumping to this proposition because of shortage of time. Because other things are not that important. This is the important bit. So the continuity of f at any point C is equivalent to the condition that limit of f at C should be equal to functional value at C. Okay, so if functional value is equal to the limit of that function, then we say that the function's limit is, so the function is continuous. Okay, so this is the definition for a function being continuous. So we say a function is continuous on an interval a to b if the limit for all interior points is equal to functional value, the right hand limit is equal to functional value at the left boundary. So I'm saying that there's some boundary a to b over which I'm defining some function like this. So this function is continuous if limit at a plus, that functional values to the right of a is equal to functional value at a. The limit at b minus, that is limit or the functional values to the left of b should be equal to functional value at b. And for any interior point, the normal limit definition applies. So for all points between a and b, that is for all interior points, the functional value should be equal to limit, and otherwise this should be the case. Okay, so let's look at quickly at some example here. So suppose I am looking at limit suppose I'm looking at function f of x equals to, let's say x times x minus 3 upon x minus 3 for x not equal to 3 and some value b at or for x equal to 3. Okay. So most of the questions on continuity will be based like this, that find b such that f of x becomes continuous. And this is going to be the most common type of questions. So you have to find limit x tending to 3 f of x. Okay, so what happens to this thing as x tends to 3? So as x tends to 3, I know that x minus 3 upon x minus 3 will cancel out, and you'll be left with x. So these two things cancel out. So this is just going to be limit x tending to 3x, which is equal to 3. So if b was actually equal to 3, then my function would have been continuous. Okay. So the bottom line is that if you have a question of the format like this, suppose instead of giving the function, he just gives you some random function h of x for x not equals to 3 and some constant value b for at a. So suppose we are looking at some value of x around a. So he says that when x is not equal to a, the function follows some function h of x. This h of x was this thing right now. It could be something else in some other question. And at a, the functional value is b. So you have to find b such that the function becomes continuous. So in this case, you always have to find limit x tending to a f h of x. And whatever that value is, it should be equal to b. Okay. So to look at this function, suppose again, the graph of this function will look like this actually. At 3, there's going to be a discontinuity. Everywhere else, it will look like y equals to x function. But at 3, this function is discontinuous. So if I were to define this function as equal to 3 at 3, then this function becomes discontinuous. It's like this function is a road, a straight road which had a pothole. I take some filling material and fill this pothole. Okay, and then I can remove this discontinuity. But I cannot remove a discontinuity which is essentially a jump discontinuity like the Signum function. So Signum function looks like this. Okay, so to the positive side it is +1, to the negative side it is -1. So basically the right hand and left hand limits are different. So you cannot just plug this hole and make it continuous. Okay, you cannot plug it. So it's like the gap between two mountains. So this is the peak and this is the starting point. You cannot plug this. But if it's a road with a small pothole, you can plug it. So this is essentially, you can imagine what I'm doing here. So there was a small pothole here. Everywhere else it was no problem, continuous. So I plugged this pothole by defining this function as the value of the limit at this point, and then this function becomes continuous. But in the Signum function, I cannot do this. So this discontinuity cannot be removed. Okay. So this is going to be about limits. Okay, I'm going to take one lecture on asymptotes this week. Why don't you guys go through asymptotes? This PDF is already uploaded here. Okay, so do the problems on limits, obviously. So we have these problem sets as before. So we have limits 1 and limits 2. So we have 2 problem sets. Just do the shaded bits. These are important. I'm only going to discuss these ones. I'm not going to discuss the other ones. They are not important. I don't want you wasting too much time. Rather than doing more problems, it's better to do the same problems again. And then we have these problems. So you have to do these till question number 11. Do not use L'Hopital. Okay, I don't want you guys using L'Hopital. So you can do these problems, that is sufficient. And read about this integration. Sorry, not integration. So asymptotes. Read about asymptotes. What are asymptotes? Okay. Yeah. So if it makes no sense at all, I'll be willing to take a lecture on this. Asymptotes is not a very important topic. They have not asked any question about it. So I don't want you to waste a lot of time on it right now, but it is important because some of you were asking about how to make graphs. So if you want to be able to make graphs of functions, then you need to know asymptotes. So read about it. If anybody is interested, if you have doubts, I can take a class on asymptotes, or maybe I can share the recordings for last year if I can find them. Otherwise, I'll take a class, no problem. But I'll take it on weekday. I don't want to take a weekend lecture because I don't know if everybody would be willing to attend a class on asymptotes. So it will be a doubt session that we take sometime, maybe Friday. So these are going to be the problems that you have to do. Yes, Kritika. Okay.
No, thanks.
Okay, no problem. All right, so that's it about limits. Do the problems, and then next week I'll share a test on limits for you guys.
Excuse me, sir.
Yeah.
So where can we find the solutions for the problem set of micro consumer theory? Question number 2 and question number 3.
Question number 2 and 3. I think I've discussed question number 2 completely, right?
Yes, so you discussed question number 2, but we are not able to do question number 3.
Okay, then I'll discuss it tomorrow. It's an important question. I'll discuss it
sir.
completely tomorrow. I don't think I have solutions for those, so I'll discuss them. Okay. All right, so I'll see you guys tomorrow at 11 o'clock for the doubt session on micro. And after that, we'll take a lecture in the evening. Ending the class now.